In today's lesson, we're going to look at the graphical interpretation of the first derivative, meaning that there must be a second derivative as well. So you've actually been working with the first derivative so far. And so let's see. We know that when we work at the derivative, we're working at the gradient of the tangent. So let's just look at the gradient. Tangent is a straight line. So let's just look at the straight line. We know that when the gradient is negative, then the function will be decreasing. In other words, as x is increasing here, what is happening to our y is decreasing. And in this case here, the gradient is positive. So if this was a tangent to a curve, the gradient is positive, and the function would be increasing. And if you can just see this line itself, why is it increasing this line? Because as x is increasing, so is y also increasing. Let's look at this graph here. We read from left to right, as it says there. So from this point, you can see that the function is increasing. The y values are increasing as x is increasing. Here, the y values are constant. Even though x is increasing, y remains constant. So it's constant there. Notice there's a horizontal line. The line is horizontal. It's constant there. And then from this point here, you can see the function is increasing. And again, from this point, going this way, the function is decreasing. So decreasing, notice the gradient is negative. Increasing, the gradient is positive. Constant, the gradient is 0. Let's look at graphs, curves more so. These are all graphs on top here, but let's look at a curve here. So if I look at this curve here, on this side, if I were to draw any tangent on this side here, the gradient would be negative. And the function, you can see it's decreasing. When I get to this point here, if I were to draw a tangent here, it would be horizontal. If I draw a tangent anywhere here, on this part of the graph, the gradient would be positive. Any tangent drawn here would have a positive gradient. The function is increasing. Again, at this point, if I were to draw a tangent to the graph at this point, it would be horizontal. And on this side, if I were to draw a tangent anywhere here, that gradient of the tangent would be positive. Now let's look at graphs that you will see more often, and this is a cubic graph. And so if I were to draw a tangent anywhere on this point here, along the graph, along this side here, it would have a positive gradient. Note, positive gradient, the function is increasing. Draw a horizontal here. At that point, the tangent would be horizontal. If I drew a tangent at this point to this function, the gradient would be 0. Anywhere here between these 2 points, x equal to 2 and x equal to 4, if I were to draw a tangent here, anywhere, any of these at any point between 2 and 4, the gradient of the tangent would be negative. Note the function is decreasing. And similarly over here, if I drew a tangent here, it would be horizontal. And on this side, if I drew a tangent anywhere, let's say at x equal to 5.2, if I drew a tangent there at x equal to 5.2, that gradient would be positive. And all along here, anywhere along here, you can see that the function is increasing. So if I were to summarize, how does this connect with derivative? The gradient is the derivative of the curve at a particular point. Then if that gradient is positive, okay, if the gradient is positive, let's say at that point 5, x equal to 5, the gradient would be positive. Gradient of the tangent would be positive. Then the function is increasing at that point x equal to 5. Similar to if the gradient of a tangent is negative, then the function is decreasing at that point. So let's take this here. Let's take the point here, let's say 2.5. If I were to draw a tangent at that point 2.5, the gradient at 2.5 would be negative, and we say the function is decreasing at that point, as in this case at x equal to 2.5. If the gradient of the tangent is equal to 0, then the function has a stationary point. So here at this point, if the gradient is equal to 0, the gradient of the tangent, this point is called a stationary point. So if I work at f dash of 4, I'll get an answer of 0, and that would imply that this point at x equal to 4, that point is a stationary point. Similarly to at 2, if I drew a horizontal line here, the gradient is 0. Gradient being 0 means that I have a stationary point at that point. Well, it looks almost at point 2 there, somewhere around there. Okay, so that's the important aspects here, that we can actually interpret the graph where it's increasing based on the derivative, where it's decreasing, and where we have stationary points. Okay, these stationary points, this one here is also called a local minimum, that's called the local maximum, and we'll talk about that later when we come to the second derivative. So let's look at an example. Let's say the sketch represents this cubic function here, 2x cubed minus 3x squared minus 12x. Determined by calculation whether f is increasing or decreasing at the following points. So obviously if we didn't have to do by calculation, visually we can see the function is increasing here because the gradient of a tangent at this any side here, the gradient would be positive. Here the gradient is going to be 0, and anywhere along this part here of the curve, if I draw a tangent here, the gradient is negative and the function is decreasing. So let's look how we would do it by means of calculation. So remember, interpreting the function where it's increasing or decreasing or stationary is to do with the derivative, the first derivative. So my function is given as f of x is equal to 2x cubed minus 3x squared minus 12x. So I'm going to work out the first derivative. So we apply our rules. The exponent gets multiplied by the coefficient is 6, and it becomes 1 less. So 6x squared, 2 times minus 3 is minus 6, and 1 less. The exponent becomes, and 1 times minus 12 is minus 12, and 1 less the exponent. So there's my gradient of my tangent anyway. But they ask me to determine whether the function is increasing at the point x equal to minus 2. So I'm going to substitute minus 2 into the gradient function. And if I substitute it correctly, I'll get an answer of 24. So in other words, at x equal to minus 2, if I were to draw a tangent here, the gradient would be 24, which is greater than 0. So when the gradient value is greater than 0, then we say that the function is increasing at x equal to minus 2. What happens at the point x equal to 0? Now we know we can see it all graphically, but if we do the calculations, so what's the gradient value when x is 0? So you plug 0 into the gradient function, you get a value of negative 12. Negative 12 is obviously less than 0. So when the derivative is negative, the function is decreasing at that point. And of course we can do it for minus 1, same principle. The question is asked, is it increasing or decreasing at that point? So I substitute minus 1 into the gradient function, and I get 0. So when the gradient is 0, at that point we have a stationary point. Okay, you can see here on our sketch, minus 1. Yes, if I do a tangent there, the gradient of the tangent would be 0, showing it's a stationary point. So what do we say? And this part I've highlighted because this is a sort of a controversial section here, in that there are two different opinions. And I'm going to go with your textbook because you're going to check your answers according to the textbook. But after I've explained it, you can decide how you want to interpret it. So we know this point is stationary. So here they say that f is increasing before the stationary point, yes, and it's decreasing after the stationary point. So we say f is both increasing and decreasing at the stationary point. However, the other opinion is that it neither increases nor decreases there. It is stationary. Okay, your textbook goes with this here, that at the stationary point, When it's increasing before and decreasing afterwards, then we say it's both increasing and decreasing at the stationary point. Let's look at stationary points then. How do we determine the stationary points? We know that at the stationary point, the gradient of the tangent is equal to 0. So in order to calculate the coordinates of the stationary points of the function, you let the gradient equal to 0 and solve for x. And once you have x, you substitute that value into the original function because that is y. Remember, this is not y, this is the gradient. So here, look at the example. Here we have the cubic function, which is represented in the sketch here. Calculate the coordinates of the stationary points of f. So let's do that first. So we know for stationary points, we're going to put the derivative of this function equal to 0. So let's find the derivative using our rules. So it's minus 3x squared plus 12x minus 9. If I apply my rules for differentiation here, that's a constant, so it's 0. So to find the stationary points, you put the gradient function equal to 0. We can divide throughout by 3 here. Divide the left-hand side by 3 and the right-hand side by 3. Factorize, you get x minus 1 and x minus 3 equal to 0. And therefore x is equal to 1 or x is equal to 3. So in other words, at x equal to 1 and x equal to 3, we have stationary points. And so to find the corresponding y value, because they asked me the coordinates, I substitute x equal to 1 into y. This is y, not that, that's the gradient. So substitute 1 into this, and if you do the substitution correctly, you should get minus 1. So my stationary points, my coordinates of my stationary points is 1 and negative 1. Now do the other one, x equal to 3, substitute into y. So you're going to replace x with 3. Wherever you see an x, you substitute the value 3. Substitute into the f of x. You get an answer of 3. So my other stationary point is x is 3 and y is 3. So in other words, here's my one stationary point. The coordinates is 1 and minus 1. The other stationary point is x is 3 and y is 3. Now the question then asks further, for which values of x is f increasing and where is it decreasing? So you can see here it's increasing between these two stationary points. So we write our answer that x is more than or equal to 1 but less than or equal to 3. We could, however, write it like this: x is more than 1 but less than 3. Remember I said there's a difference of opinion. In this case, the stationary points are included. And where is it decreasing? So the function is decreasing here. Again, if I drew any tangent along here, the gradient would be negative, and that's where the function is decreasing. So it's decreasing before that point. And again, here you can see the function also decreases there. Draw a tangent anywhere along the side, the gradient would be negative. So to answer the question, where is the function decreasing? It's less than or equal to 1. It's on this side of 1, and it is on that side of 3. So that's why the or to separate intervals. Again, notice it could have been written like this because of the difference of opinion where the stationary points are excluded.